Welcome everyone. In this video lecture, we will solve a GATE 2010 analog circuit question in which we have to find out the I node current. We have to find the I node current, and this is a current mirror circuit. It looks like a current mirror circuit, but in this question, it is given the emitter area of transistor Q1 is half times of emitter area of Q2. So the given things are the emitter area. So I am writing emitter area. So AE1 is nothing but simply half times of AE2. It is given in our question. Emitter area of transistor Q1 is half that of transistor Q2. So this one is the given thing, and we have to find the value of I node current in the circuit. Okay, so it looks current mirror circuit. So one can say if the current is in this one, if the current is say I1, then I1 is nearly equals to I naught. Okay, in simple current mirror circuit. But we can't say directly this I1 equals to I naught because we are dealing with some area concept of the emitter. Emitter area, if the emitter area will be constant, it may be same. But here there is a change in emitter area. So how to solve such problem? So in such case, we have to first think about a closed loop, that is our say this loop say 1. Okay, and in this loop we have to go for the KVL. Okay, so this one is nothing but simply VBE 1 voltage and plus or minus VBE2. So basically in this loop we have to find out the KVL. Okay, so this concept is called the translinear principal concept. So I am not discussing the translinear principal concept. So translinear concept, or we can say simply, in such question we have to just apply the Kirchhoff's voltage law in the closed loop, this closed loop. So one can simply write the equation for this one, KVL. So we have to write KVL in loop 1. Okay, KVL in loop 1. So one can write plus VBE1 plus VBE1 minus VBE2 equals to 0. Okay, minus, so one can write simply our VBE1 equals to VBE2, both having the both transistor Q1 and Q2, the base emitter voltage will be same. Okay, now next, now we are very familiar, say this one is our equation number 1. Okay, now we are very familiar with a very well known formula for say the collector current IC equals to IS EXP VBE by VD. Okay, so now this collector current, this one is nothing but simply our say the collector. Okay, collector one, this one is base one, and this end is emitter one. Okay, so IC equals to the collector current saturation current into exp vpe by vt. Okay, so in this one, one can write the value of vbe. So one can write, I am just writing the step by step procedure. Is exp vbe by vt. Okay, one can also write this vbe by vt equals to ln IC by IS. Okay, so finally, what we can write, the value of V, sorry, IC by IS, okay, and this VBE is nothing but simply VT ln IC by IS. Is it okay? We can write this VB value, we can write this VB value H VT ln IC by IS. So now next, what we can write this VBE1 is nothing but simply from equation 1. I am writing here from equation 1 we can write this VBE is nothing but simply VT. Okay, this one is the thermal voltage, so VT. Okay, so it will be VT, then ln, and IC is nothing but simply for the timing I am saying I1. So better to write I1 by saturation current, say IS. So one can write as IS1. Okay, and this VBE2 due to this transistor we can write it the collector current. So this collector current is nothing but simply our I naught. So one can also write this is equals to VT ln I naught by IS2. Okay, so this VT will be cancel out, and this will be equals to I1 by IS1 equals to I naught by IS2. Okay, in current mirror concept, this thing we have to apply translinear principle, and how we have to proceed in how we have to proceed. This one is the process. Okay, so now what we have to find the value of I naught. So one can write I naught is nothing but simply I1 into IS2 by IS1. Okay, I naught equals to I1 IS2 into IS1. So for this one, we have to find the value of I1. Okay, clear? Now, so for the timing I am writing this one is I1, and very important relationship is given. Okay, this emitter area. So that thing, the saturation current. Okay, the saturation current. Okay, saturation current, clear, is, this is is proportion to the emitter area area emitter area we can say. Okay, this is is always proportional to the emitter area. This is very important concept, otherwise you have to use the whole formula for saturation current. But if you know little bit about the saturation current, the this is value is somehow proportional to the area. So is2, if the emitter area of is2 is, or we can write as some constant factor, proportionality constant k, and some area, so we can write as a. Okay, area. So Is equals to, suppose for the S1 transistor, we can write Ia E1. So Is2 is nothing but simply we can write some constant factor, say K into A E2 by K times of A E1. Okay, so this K and K will be cancelled, and this I1 equals to AE2 by AE1. Now AE2 by AE1 we can write from this equation. AE2 is nothing but twice times of AE1, so we can write as this one twice AE1 by AE1. So this AE1 cancel out, so we can write I naught equals to twice times of I1. I naught equals to twice times of I1. We have used the given things, emitter area of transistor Q2, Q1 is half as that of Q2. So IS2 will be twice times of I1. Okay, so now if we know the value of I1, we can get the value of I naught. So for this purpose, what we have to do? So for this purpose, what we have to do? We have to apply the Kirchhoff's voltage law in this section. Okay, say this one is a loop 2. Okay, and this one is nothing but simply our 10 volt. So this one is minus plus. We can also write this one. So it can be written as 10 volt. So we have to write the Kirchhoff's voltage law in this loop. So what do we have to write? Okay, I am writing here. Okay, so how to write the equation for this one? Because this one is I1 current is given. So now what we have to write KVL in loop 2. Okay, so it will start from here. So one can write, okay, I'm taking black pen, minus I1 into 9.3 into 10 to power 3. Okay, you can change the notation, a minus or plus, depending upon your how you are using the convention methods to solving KVL KCL. Okay, I am using current action in the same in the resistance. I am taking minus here. Okay, then there will be this one will be sorted, not issue. Then plus minus VBE1. Okay, so what we can write, minus VBE1. Now this voltage is minus VBE1. Then this minus and plus, it is coming from plus. Okay, so plus 10 equals to 0. Okay, very simple. I1 9.3 10 to power 3 kilo. Okay, minus VBE1. Okay, this voltage we have to take care. Okay, means, or in a general way we can say we are using this Kirchhoff's voltage law in that side. Okay, same thing. Okay, so now everything is there. So from here we can easily find the value of I1 as I1 into 9.3 into 10 to power 3. Okay, we are keeping in the right hand side, or okay, and equals to 10 minus VBE1. Okay, so one can write I1 into 9.3 into 10 to power 3 equals to 10 minus 0.7. Okay, so this I1 is nothing but simply 9.3 by 9.3 into 10 to power 3. Okay, so it is nothing but simply our 1 milliampere. Okay, very simple calculation is there, but we have to know the some network theory concept, some how to use the KVL, where we have to use. Okay, by solving such type of question, you will become expert. Okay, so now the value of I1 is 1 milliampere. Now one can say I1 is 1 milliampere, so this one will be I naught will be 1 milliampere. No, because the emitter area is changed, so emitter area will change the this I naught current. So now we have the relationship between I naught and I1. So I1 is nothing but simply 1 milliampere. So the I naught value will be twice into 1 milliampere. So it should be 2 milliampere. So we can say the final answer is 2 milliampere. Is it okay? So our answer for this question will be 2 milliampere. Okay. So what are the means key step? Our given thing, that is our emitter area of AE1 is twice times of AE2, and we have to find the value of I naught. I have already. Okay. So after that, what we have to do? What we have to do? We have to use KVL in this loop. Okay. So one can say VBE1 equals to VBE2. Okay, very simple. KVL is there. Okay, now we know one relationship. Okay, IC, collector current, equals to IS EXP VBE by VT. Okay, from there we can write this VB equation. Okay, now this VB is there, so corresponding VBE1 and VBE2 we can simply write. Okay, by writing this two term. Okay, in left hand side, right hand side. Now this VT will be constant thermal voltage, so it will give the value of IS1 and IS2. I1 and IS1 equals to I naught by IS2 we can write. Okay, now the main important thing is given. This IS is nothing but simply proportional to area, emitter area. So IS1 is K times of AE1 we can write. So IS1, now I naught equals to I1 into IS2 by IS1. Now this IS2 is nothing but simply K times of area of emitter area. Okay, so AE2 and K times of AE1, and it is given AE2 is nothing but simply twice times of area 1. Okay, so finally we get the I naught and I1 relationship, that is our I naught equals to 2 times of I1. After that, if you get the value of I1, we can easily say I naught value. So for this purpose, what we are doing, we have to apply Kirchhoff's voltage law in this loop. Okay, Kirchhoff's voltage law in this loop. So how we have to write the equation? We have to simply write equation that minus I1 9.3 into 10 power 3 minus VB1 plus minus, so minus VB1 plus 10 volt. Okay, equals to 0. So if we solve this one, it will simply give the value of I1 as a 1 milliampere. Then finally I1, we have the value of I1. So by putting this I naught value in this one, we will get the value of I naught as a 2 milliampere. So this one is the simple numerical, but so many things are there. Okay, but we have to know the basic concept, means KVL or some collector current equation. Okay, and the relationship between IS and emitter area. Then we have to club all together, so we can find the value of. So we have already find the value of I naught, which is 2 milliampere. So this one is the concept about this numerical. So thank you for watching, and please subscribe my channel. Thank you.